Now we are going to study a very important concept in mathematics, which is widely used in calculus and other branches of mathematics. Functions. Functions. Now, what is a function? Already we are familiar with the relation from a set A to another set B. If A is a set and B is another set, say A and B respectively, then we can define a relation from A to B by taking some of the pairs, ordered pairs AB, where A is from A and B is from B. Such a collection is a relation from A to B. In short, actually, a relation from A to B is a subset of A cross B. It is a subset of A cross B, the Cartesian product of the two sets. So, any subset of A cross B is a relation from A to B. Now, function is a kind of relation satisfying certain conditions. What are those conditions? Before going to the condition, let us take some example and we'll see which of the relations that we are going to define are functions. Now, let us take A is equal to set 1, 2, 3 and B is equal to set AB. Any subset of A cross B is a relation. Now, I define R1 from A to B, a relation which consists of the pairs like 1A, 1B, 2A. Another relation R2 from A to B, which is equal to a set 1A, 1B, 2A, 3B. Another relation R3 from A to B, which consists of the pairs 1A, 2A, 3A. Now, a fourth relation from A to B by 2A, 3B. Okay, that's all. That's enough. Now, is R1 a function? Now, function is a relation from A to B such that every element of A uniquely comes in one of the pairs of the relation. Say A consists of the elements 1, 2, 3. Every element of A must have image in B. That means when we are writing in the tabular form, every element of A must come in the first position of the pairs of the relation. Let us examine whether R1 is a function or not. A consists of the elements 1, 2, 3. Of course, 1 has come in the first position of the first pair, but 1 is repeatedly come in the second pair also. Therefore, this cannot be a function, because 1 has two images here. A and B are the images of 1. This is not allowed in function. Now, what about R2 from A to B? Here you can see that 1 is associated with A, 2 is associated with A, 3 is associated with B. But here again, 1 is associated with another element B. That means 1 has come here repeatedly in two pairs. Therefore, this is not a function. Now, what about R3? It consists of the pairs 1A, 2A, 3B. Now, every element 1 is in some pairs as first element, of course, 1, 2, 3. And no element of A has repeatedly come in any of the pairs. And therefore, the condition is satisfied. That means a function is a relation from A to B. A function from A to B is a relation from A to B such that every element of A has uniquely associated with some elements of B. That is, has unique image in B. That is, every element if you take here that must be associated with a unique y in B. Such a way, if there is an association or relation from A to B, then it is a function. So R3 conditions are satisfied, therefore this is a function. What about R4? Of course, 1, 2, 3 are the elements of A, but here 1 has no image here. Every element has no image. That condition is not satisfied. So this is not a function. Now we are going to write the definition of a function. A function f from A to B is a relation from A to B such that every element of A has a unique image, or one and only one image, has one and only one image in B. Or in other words, if you write f as in the tabular form as pairs, like these pairs, then every element of A should come in the first position in some pairs, and no element of A comes repeatedly in any of the pairs. Such a tabular form of relation is a function. Now let us see some more examples. I am writing A equal to 1, 2, 3, 4 and B is equal to 0, 1, 2, 3, 4. Then I am writing a relation from A to B which consists of the pairs x, y such that y equal to x minus 1. Is this relation a function? Let it this be R1. Now see if every element has image in B and whether any element repeatedly comes in the first position, that means whether it has more than one image in B. Now if you write the tabular form of this R1, it is the when you write this in the roster form, in the tabular form, this given is a set builder form. When you write this in the tabular form, what are the elements of these relations? You see, all pairs x, y such that y is equal to x minus 1. You take x is equal to 1 first, then 1 is associated with 1 minus 1, that is 0. 2 is associated with 2 minus 1, 1. 3 is associated with 3 minus 1, 2. 4 is associated with 4 minus 1, 3. Now examine whether all the elements have image in B. Yes, 1 has image in B, 2 has image in B, 3 and 4 also have images in B. And therefore, this R1 from A to B is a function. Let us take another example, R2 from the same sets A to B by set of all x, y such that y is equal to x square. Y is equal to x square. Now write the tabular form of this relation, which is consisting of the pairs 1 square. Actually, image is its square. Y is actually x square, or you can write xx square. So here 1 has image because 1 square is 1. So elements are 1, 1. 2 has image 4, but 3, its square is 9. There is no 9 in B, so 3 has no image. Similarly, 4 also has no image in B. So R2 consists of only 2 pairs, and every element in A has no image here. Every element has no. Only 2 elements, 1 and 2 have images in B, but no 3 and 4. Therefore, this is not a function. This is a function, whereas this is not a function. Now let us define another function R3 from A to B by set of all the pairs xy such that y is equal to x plus 1. Y is equal to x plus 1. When you try to write the pairs in tabular form, what are the elements? Let us see. The image of y, x is y, which is x plus 1. So the image of 1 is 1 plus 1, 2. 1, 2, of course 2 is here. 2 has image because 2 is associated with 3. 2 plus 1, 3. 3 is associated with 4. But 4 has no image here because the image should be 5 here, x plus 1. But 5 is not an element of B. So here 4 has no image in B. So every element has no image in B, and therefore this is not a function. So R1 is a function, R2 is not a function, R3 is not a function. Now let us take another example. Let A equal to consist of the elements minus 1, 1, 0, 2, like that. Then B consists of 0, 1, 2, 3, 4, like that. Now you define a function or relation first in such a way that every element is associated with squares. So minus 1 is associated with 1, 1 is also associated with square 1, 0 is associated with the 0 square, that is 0, 2 is associated with square 4. So now I am writing in the tabular form. These are consist of the elements minus 1, 1, 1, 1, 0, 0, 2, 4. Now is this R a relation, function? Let us see. Here every element minus 1, 1, 0, 2 has images because minus 1 has an image here 1. 1 also has the same image 1, that is allowed. 0 has 0 image, 2 has 4 image. Therefore this R is a function, So we have seen many examples of functions. Again I am repeating what is a function. Function is a relation in such a way that every element of that first set, that is A, has unique image in B. Function can also be said in another way. Function is a rule actually. Function from a set A to another set B is a rule. It is a rule. That rule assigns, is a rule that assigns, that gives, that assigns to every element of A, a unique element of B. So without mentioning relation, we can define function like this. Function is a rule. It is a rule that assigns to every element of A unique element of B. For example, here, consider 1, 2, 3 here. If every element is associated with some element, unique element, some A, 2 is associated with B, 3 can be associated with B, there can be another element C here, no problem. Now this is a function. Here when you write the function in tabular form, it consists of the pairs 1A, then 2B, then 3B. Here every element 1, 2, 3 has image. That means every element has come in the first position of the pairs, some pairs, and no element of A has repeatedly come here. Therefore, this is clearly a function. Whereas I am drawing another picture, the same sets A and B. A consists of 1, 2, 3, and B consists of A, B, C. I am taking 1 to A, again I am taking 1 to B, 2 to C, and 3, let it be 3 to B, no problem. So the pairs are actually 1A, then 1B, then 2C, 3b. Here, every element has come. Every element has image, but the element 1 has 2 images here. So this is not allowed. This is not allowed. 1 is associated with A, at the same time 1 is associated with B, that is not allowed. Whereas here you see 2 is associated with B, 3 is also associated with B. This is allowed in a function. That is, distinct elements in A can have same image in B. But an element in A cannot have distinct images in B for a function, for it to be a function. So here this is not a function because here one has 2 distinct images here. That is not allowed. It must be unique. Image of under this function should be a unique. Then only it can be a function. Now let us go to what is domain and range of the function. Domain and range of the function. Already we are familiar with the domain and range of a relation. If f is a function from A to B, by the definition of the function itself, you can see that every element of A has image in B. Every element. That means when you draw a picture like this, every element here has image, some image here. And therefore, the domain of this function is always A. So, if f is a function from A to B, its domain is the whole set A. The whole set A. Whereas range means the range of the function or relation is defined as set of all y such that xy is in R, is in that relation or F. This is range. Range of a function is set of all y such that xy is in F. That is, set of all the second elements of the pairs of F is range, or set of all images, you can say. The range is set of all images. All images. Let us take an example. -2, -1, 0, 1, 2. We are defining a function from this set to another set. Let this be P, this is Q. I am defining 0, 1, 2, 3, 4. -2 is associated with 4. -1 is associated with 1. 1 is also associated with 1. 2 is associated with 4. 0 is associated with this. That means every element x is taken to its square x. Its square. Image of x is x square. Or this function we can write algebraically as fx is equal to x square, where x in P. X in P. This is how we define algebraically this function fx. Every element is taken to its square. Now the domain of this function, domain of f is the whole P. And what about the range of the function f? Range of the function consists of 0, 1 and 4 images. That means the squares of these elements in P. For 0, 1, 4. You see that 0, 1, 4 is clearly a proper subset of Q in this case. So range is normally, range if you take, that the range of a function is always a proper, it's a subset of B. A function f, if f is a function from A to B, then range of f is a subset of B. It can be equal to B. In that case, that function is we will call later onto function or a surjective function. If the whole B is its range, we call it onto function. So domain and range. Now let us take another example and let f a equal to something like let it be a subset of R, or you could consider the function f from R to R by f of x you take as x plus 3 or y is equal to x plus 3. This is a function of x. Fx is the image of x under where x belongs to R. This is R, this also R. Every x is taken to x plus 3. Now this is clearly a function because every element x has x plus 3. There is also a real number, no? If x is a real number, then x plus 3 is also a real number. That means it's a clearly a function. Now what about the domain of this function? R. Range of the function is also R, the whole R. Instead, I am restricting this domain as something like all the real numbers in between -1 and 1, like this, or -1 less than or equal to x less than or equal to 1. Suppose this is our a, and we are defining a function f from a to r by f of x is equal to x square, f of x is equal to x square, or y is equal to x square. Now, what is the domain of f? What is the range of f? Let us see. Here the domain is the whole set A, because it is a function, clearly well defined function. Every element in x has its square in R. That is clear. This is A, this is R. This consists of all the numbers from -1 to 1, and R consists of all the real numbers. So whatever x if you take here, it has a square x. That's clearly a real number. Its square is a real number that varies from, actually this numbers varies from 0 to 1. 0 to 1. Since x is from -1 to 1, its square is varies from 0 to 1. 0 less than or equal to x less than or equal to 1. And therefore, the range of this function is the closed interval 0, 1. Closed interval 0, 1. Domain is the closed interval -1, 1. Or all the real numbers in between -1 and 1, including -1 and 1. Range of f is 0, 1. Okay, now let us take another example. Suppose f is a function consisting of the pairs like -1 to 0, 3, 2, 4, 1, 5, 1, 5. Now what is the domain of f? Domain of f is consisting of -1, 0, 2, 1, set of all first elements of the pairs. Range of f is 2, 3, 4, 5. 2, 3, 4, 5. Second element, second the set of all y's, that is range. Now this is already given a function, so there is no suspicion here that whether it is whether every element has image. No, such question doesn't arise because it is already given that f is a function. We are suspecting that whether it is a function only when a is defined. A is defined. There we have to see whether every element in A has image in B. Such things to be tested here. But there is no question of testing here because already it is given as a function from A to B, -1 to 0, 3. If it is a relation from given, then it is not that much easy unless this A is clearly mentioned. If A is not mentioned, we cannot say whether it's a function or not. Okay. So that's about the domain and range. Now we will see some particular real valued functions. What is actually real valued functions? Real valued function. A real valued function is a function from set of real numbers to another set of real numbers. A subset may be, if A and B are subsets of real numbers and f is a function from A to B, then it is a real valued function defined on real numbers. Now there can be real valued function even if this A is not a subset of R and B is a subset of R and f is a function from A to B, then also we call it real valued. But as far as you people are concerned, we are concerned with only subsets of real numbers. There may be complex numbers here from A and that may be associated with some real number. For such way we can define function from A to B. But here it is not like that. Here we are concerned with subsets, all are subsets of real numbers. So real valued function is the value is real, that's all. A function from A to B is real valued if the range of f is a subset of R, that's all. Range of f is a subset of R. That means set of all images should come from a subset of real numbers. Subset of real numbers, that is real valued function. But the domain is also here. For the time being, we will take as a subset of R, that's all. Now there is a real valued function. Now let us take some functions from R to R, very important certain functions. That function, we call it, one first important function is identity function. Identity function. A function from R to R, defined by f of x is equal to x. That is, fx is equal to x. Fx is equal to x. That is, every x is in R, every x in R is taken to x itself. Such a function is called identity function. Now, since functions consist of the pairs xx here, xx here, where every x in R, we can plot these points on a graph sheet or a plane. We can plot by choosing the proper Cartesian coordinate system, by properly choosing x scale and y scale for x-axis and y-axis. Then we can plot this xx. When you plot xx here, what do you get? If you take an x here, then its image is also x here. So we'll plot the point xx like this. If you take another x dash, you take its image is the same x dash. So we'll plot here. This way, if you take 4 here, for example, minus 4 here, then its image is also minus 4. So the point is here. So considering all these points and draw a graph like this. This is the graph of the function. We say that's a straight line passing through origin. This is origin. It's a straight line passing through origin. So the graph of the function fx is equal to x is a function, is a straight line passing through the origin, which is inclined at an angle 45 degree, pi by 4 radian. This function is called identity function. Now many other such functions are there. Another important function is quadratic function. A particular quadratic function, call it fx is equal to x square. We call it, it's a parabolic function. Parabolic function. That is, you consider the function f from R to R defined by f of x is equal to x square. That means it consists of all the pairs x square, where x in R. Now if you try to draw the graph as before, what happens? When you draw the graph, here 0 is an element, so 0 is image of 0 is 0. Actually, normally to draw the graph, we take some tabular table. We construct a table here by taking x values and y values. You take some x as minus 3, minus 2. Of course, in between minus 3 and minus 2 are here, because every real number is in the domain. So, but for the drawing purpose, we take the integer type values for x for the time being. Minus 1, 0, 1, 2, 3 like that we take. And you compute the corresponding y values like this. Its square, every element has image as its square. So minus 3 square is 9, minus 2 square is 4, 1 here 0, 1, 4, 9. So the points on this graph of the function are, some of the points are minus 3, 9, minus 2, 4. Don't think that these are the only points. In between many points are there. 2, 4, 3, 9 like that. Now you plot these points here on using a special coordinate system here, Cartesian coordinate system. 0, 0 is a point here, 0, 0. So this is one of the points. Then 1, 1 is there, minus 1, 1 is there. This is minus 1, this is 1. So its image is 1 here, this is 1. So this point is there. Then minus 2 and 2 has the same image 4. So this is minus 2, this is plus 2. Its image is 4 actually. I am producing this line. This is 1, 2, 3, 4, somewhere, let it be somewhere here. then minus to 4, this is the image, this is the point corresponding to that. Now imagine all the points, 3, 9, minus 3, 9, 9 is there. So imagine all the points and you freely draw a curve passing through all these points. You get a curve like this, and this is called parabola. So this is a parabolic function, fx is equal to x square. So for drawing graph of a function, we normally consider integers and or the purpose of easiness. See, drawing easiness, of drawing, we take only the integers, minus 3, minus 2, minus 1, 0, 1, 2, 3, etc. Actually, in between minus 2 and minus 1, there is a minus 3 by 2. Minus 3 by 2 square is 9 by 4. There is a point somewhere here is there, actually. So you have to mark. If you can draw freely connecting all these points, then it is very easy. If such points, so many points you have to consider, that's all. To draw, to get an approximate graph of a function, you consider some 5 or 6 points, and if you can have a clear vision of that the curve passes through these points, can freely draw, then that's enough. Actually, that is a way we draw the graph. Even otherwise, you can use, there are many drawing apps are there, like Desmos you can use, very easy to use. Desmos, using Desmos you can draw the graph of the function. I will show you what is how to draw the graph of the function using Desmos. You just type Desmos here, DSMOS, then go to that Desmos. Okay, this is the Desmos site where you can draw. Also there are apps that you can install in mobiles. So to draw the graph of the function, you just type x square here, x square. This is a x square. X square is first you take x and then you take square. So you got a graph. See here, this is the graph x square. Here the domain is set of real numbers. It is considered x square. Similarly, earlier we drew the graph x, fx equal to x. So that's a straight line like this passing through origin. This is a straight line passing through origin. If you want to see only x square, then you simply click here and you see the graph of x square only. Otherwise, you can see both curves x and x square on the same graph sheet you can find. So this is easier way to draw the graph of a function by using the Desmos app. Now, another important function is modulus function. Third one, modulus function. Modulus function. That is, f of x is equal to modulus of x, where x in the set of real numbers. That is, the domain is all the real numbers, and every element is taken to its absolute value. Modulus of x means absolute value. And you may be knowing that how we define an absolute value function. Modulus of x is defined by x, if you take x is greater than or equal to 0, or even if it is 0, it is 0, and minus x if x is less than 0. This is how we define absolute function. That is, modulus of minus 3 is 3, modulus of 4 is 4, modulus of 0 is 0. It goes like that. This is called absolute value function or modulus function. When you draw the graph of the function, you can see that every x is non-negative. If you take x greater than or equal to 0, its image is itself. That means every x is taken to x itself. So the graph goes like this, because every x, 1 has image 1, 2 has image 2. Whereas if x is negative, that is minus 2 has image 2, minus 3 has image 3. So if you take a minus 2 here, its image is 2, minus 3 if you take here. So the graph goes like this. It is a V-shaped curve. V-shaped curve. Graph of this modulus function is a V-shaped curve. This also you can see in the using Desmos. There is, I am taking absolute value of x here, absolute value of x. See here, this is the graph of the function. It's a V-shaped curve. This angle is 45 and this angle is also 45 in that sense. Actually it is 135. Okay, now let us take another important example. Fx is equal to e raised to x, exponential function is there, logarithmic function is there. Now a constant function let us take, that is fourth one, you take as constant function, that is every x is taken to a particular constant here, x is taken to a particular constant, say some k, maybe 5, minus 3, like that. This is always fixed k. Every x changes here. Here this function is like this. This function is, every x here is taken to a unique k. Every x is taken to k only, like that. This function is called a constant function. Or we can define algebraically like fx is equal to k for every x in R, such a way. Now, if you draw the graph of this function, what happens? Every x, whatever x if you take on x-axis, wherever you take x, its image is only k. Suppose this is k, I am taking positive here. This is k. So, for this x, it is k. For this x, it is k. For this x, this is k. So, you are getting a curve or a straight line you are getting which is parallel to x-axis, horizontal line. So, the graph of the function fx is equal to k, constant function, is a horizontal line, k distance from the origin, k. If it is minus 3, that straight line will be here below x-axis. If it is minus 3, suppose fx is equal to minus 3, when you draw the graph of the function, you can see that it is here, minus 3. This is the way. So, constant function is also a straight line, but this straight line is a particular type of straight line, horizontal line, parallel to x-axis. Now, there are many other functions, polynomial functions. You can take one of the polynomials we already considered, fx is equal to x square, fx is equal to x all we have considered. A polynomial function, generally that fx may be a polynomial function, a polynomial. Polynomial is an expression, algebraic expression, something like form a0 plus a1x plus a2x square plus etc. plus anx raised to n is a polynomial of degree n if an is not equal to 0. For example, x cube minus 3x plus 8 is a polynomial, px or f of x, whatever it is. It is of degree 3, we say. It is a degree 3. It's polynomial function. If you given a polynomial function, you can compute all the images for every x. Suppose a consists of minus 1, 0, 1 and p is the polynomial function from a to r. Then you can find its images. Minus 1 is taken to, the image of minus 1 is minus 1 raised to 3 minus 3 into minus 1 plus 8. That is equal to minus 1 plus 3 plus 8, this is equal to 10. So, its image is minus 1 is taken to 10. Now, what about 0? When 0, its image is 0 cube minus 3 into 0 plus 8. So, 0 is taken to 8. 1 cube, 0 is taken to 0 cube minus 3 into 0 plus 8, which is equal to 8. And 1 is taken to 1 cube minus 3 into 1 plus 8, which is 1 minus 3 plus 8, that is 9 minus 3, which is equal to 6. So, 1 is taken to 6. So, under this function, we can compute the polynomial values of the polynomial px by assigning the values x from the domain of the function. If it is R, for every x, there is an x cube minus 3, which is a real number. This is a real number for every x. For any x in R, this px is a real number, it's an element of R. So, it is a function from R to R. A polynomial is actually a function from R to R. One of the such functions is, for example, fx is equal to x square. We already saw it is a parabola. I showed the graph. It's a parabola like this. Parabola fx is equal to x square. Fx equal to x is another such function. And the functions like f of x in the form some mx plus c you take, or ax plus b form. Ax plus b form. This type of function we normally call linear function. We call it linear function, because its graph will be a line. That is why it is called linear function. A function which takes every x to some ax plus b. It's a straight line. If you draw the graph of this function, it will be some straight line like this. Maybe like this, maybe like, depending on the slope of this straight line. So it is a straight line. That is why it is called a linear function. Then is polynomial. Suppose it is something like ax square plus bx plus c in general. Another function gx is equal to. This is called quadratic function. Second degree function we call it. Its graph will always be a parabola. Parabola may be here or here, depending on whether a is negative or like that. Not like this. It is always like this, because its axis is always will be parallel to y-axis. Such a way. So gx is equal to x square plus b is always a parabola. One particular case we have already seen, fx is equal to x square. It is a parabolic function. It is a parabola. Now fx is equal to x cube. Instead of x square, suppose the third degree x cube, it comes to only one term x cube. The graph of this function will be, you can taking some x values and y values. Y is actually x cube here by taking, for example, -3, -2, -1, 0, 1, 2, 3 like that. -2 cube, because the function is fx is equal to x cube. Now -3 cube is -27. -2 cube is -8, -1 cube is -1, 0 cube is 0, 1 cube is 1, 2 cube is 8, 3 cube is again 27. So when you draw the graph of the function, it will be a function like this. You can see that it's a function like this. This is the graph. You try to draw, that is x cube. Let us see in Desmos what is the how the graph is x cube. The graph of x cube is x raised to 3. Now this is x square cube. What I typed is wrong. 3 x cube. See the graph. This is the graph of the function x cube. So you can draw similarly the graph of x raised to 4, x raised to 5, and a pattern you will be seeing later, and in higher mathematics you will be learning how the graph goes like that. So all these are polynomial functions. Fx equal to x, fx equal to x square, fx equal to x cube. There is another function called rational function. Now what is a rational function? Already you are familiar with what is a rational number. A rational number is a number which is of the form p by q, where p and q are integers, q not equal to 0. It's a rational number. Something like 3 by 4 or -2 by 3, like that. 0 divided by 5. All these are rational numbers, but not 5 by 0, because q cannot be 0. 5 by 0 is not a rational. Root 2 by 3 is not a rational, because root 2 is not an integer. So all numerator and denominator must be integers, and denominator must not be 0. Such a number is called rational number. And what about rational function? A similar expression. That is, suppose px and qx are any two polynomials. You take, for example, x square plus 3 is a polynomial, 2x minus 5 is a polynomial. Then px divided by qx, that is x square plus 3 divided by 2x minus 5. Such a function we call rational function, provided there is a condition that here the q cannot be 0, p by q. Similarly, this qx is not equal to 0 for any x. That is 2x minus 5 should not be equal to 0. When this is equal to 0, what happens? When 2x minus 5 equal to 0, it gives you the value for x, for which it is 0. That is 2x equal to 5. and x is equal to 5 by 2. So this is clearly defined as function only if x is not equal to 2 by 5. Sorry, 5 by 2. X is not equal to 5 by 2. So x square plus 3 divided by 2x minus 5 is a function where for every x real number but not equal to 5 by 2. So this function is called a rational function. 2x divided by x square plus 3 is always a function. For all x in R, it is a function. For all x in R, real number, for every real number, this is a function because x square plus 3 is not equal to 0 for any x. Whereas if you take 2x divided by x square minus 4, then this is not a function for which, because this function is not defined for x is equal to 2. When x is equal to 2, you can see that this denominator is 0, so this is not a rational number. X is equal to minus 2, then also this is not a real number. That is, this number 2x divided by x square minus 1 is not a rational form number. Minus 2 also make it 0. So, except qx not equal to 0. So, rational function in general, what is a rational function? If px and qx are any two polynomials, then a rational function Rx is of the form px divided by q of x, provided qx not equal to 0 for any x, in the domain. There is a domain, no? Our domain should not contain any x for which qx is equal to 0. For example, suppose I am defining a function from R to R defined by f of x is equal to 2x divided by x square minus 3x. 2x divided by x square minus 3x. Question, is it a function or not? Here you can see that the denominator is 2x divided by x square minus 3x. This denominator is 0 when x is equal to 0 and x is equal to 3. But x equal to 0, if you take, we'll be seeing later in calculus that for x is equal to 0, this function has a particular value. That value you can find afterwards. So, but x is equal to 3, it make it 0, denominator equal to 0. So, this function is not defined for x is equal to 3. So, x not equal to 3, and for the time being you can take 0 also, because later you will be seeing that for x equal to 0, this limit etc. May exist. By cancelling this, you will get 2 divided by x minus 3. When x tends to 3, it has a value. When x tends to 0, it has a value. 2 divided by minus 2 by 3 you will get. You can see it later. So, this function fx is equal to 2x divided by x square minus 3. Is it a function or not? This is not a function. For which x is equal to 3, this is not a function. Because 2x divided by x square minus 3x, you can factor, denominator you can factorize as x into x minus 3. This way you can define. Now cancelling this x, you get this function is 2 divided by x minus 3. So this function is not defined only for x is equal to 3. When you draw the graph of the function x square 2x divided by x square minus 3x, you will get a graph by using Desmos. Let us take 2x, that is 2x divided by, x square minus 3. In bracket you should write x square minus 3 minus 3. See here, this is the graph. There are some points you can see where it becomes infinity and all. That means when x is equal to 3 here, it goes to infinity, and x equal to root 3 here. You can see that it goes to when x is equal to root 3 minus root 3. This function is not, actually it should be x. There should be an x here that we have taken earlier. There is an x here. So the graph is like this. So this function, when x is equal to 3 here, it goes to infinity. It is not defined. Therefore, this function is not defined, but you will still get get the graph of the function, you can find using Desmos. You can easily draw the graph. That's the rational function. So rational function is a function which is of the form px divided by qx and avoid in the domain the post points for which qx is equal to 0. You take omit all the points for which qx equal to 0. So that is rational function. There is another function called sine number function. Sine, S-I-G-N-N-U-M. Sine num function. It tells actually what is the sign of x. You take any x here, what is its sign? That is sine num function. Sine num function. If x is positive, it takes to 1. If x is negative, it takes to minus 1. If it is 0, it takes to 0. So it has only two values, minus 1, 1 and 0. The range consists of only three values, minus 1, 1 and 0. So the function is defined by SGN of x is equal to minus 1 if x is less than 0, 0 if x is equal to 0, 1 if x is greater than 0. This is how we define sine number function. And the graph of this function, you can see that for 0 it is 0, for positive it is 1, that is the graph is a straight line towards the right side from 0 at plus 1, and for x is negative it is minus 1, so minus 1. So that is the graph is to the left a straight line, a horizontal line. So this is the graph of the function here. This point is also there, 0, 0. Here 0 is not there, so we just draw a circle here because that point is not there. For 0 it is not here, only for x greater than 0 and less than 0 are on these lines. So this is the graph of the function. Such a function we can call, maybe if it is defined, something like a step function you can say. Another important real valued function is greatest integer function. This is a real valued function, that is a function from R to R. For each x in R, f of x is the greatest integer less than or equal to x. For example, suppose this is the real line here. You take any x between 2 and 3, that is from greater than or equal to and less than 3 you take for any x, then its value is 2. F of x is 2. From 1 to 2, greater than or equal to 1, less than 2, that is for 1 less than or equal to x less than 2. The function takes the value 1. For 2 less than or equal to x less than 3, it takes the value 2. For minus 1 less than or equal to x less than 0, that is in this interval for any x, it takes minus 1. This minus 1. For minus 2 less than or equal to x less than minus 1, it is minus 2. Like that it goes. When you draw the graph of the function, it will be a step function like this, because it takes 0 value, 1 value, 2 value. Similarly on the left side it is minus 1 value, so then minus 2 value, like that it goes. So it is a step function like this. So the greatest integer function is a step function. It is graph is just like a ladder, steps. Therefore we call it a great step function. So greatest integer function. Now let us move on to algebra of functions. Algebra of functions. You know, in the case of real numbers, for any a and b, if you take, we can add the real numbers, we can multiply, we can subtract a number from another number, we can divide a number by another number, unless that b is not equal to 0, of course. Then all these kinds of operations you can do on the set of real numbers. Similarly, in the case of set of functions, if you take the collection of all some functions, f and g are any two functions here. The similar operations you can do on set of functions also. That is, if f is a function from R to R, g is a function from R to R, then you can define f plus g, f minus g. Similarly, k into f, a scalar times multiple times f, then f into g and f by g. How this function is defined? For each x in the common domain of f and g. That is, f may have a domain and g may have another set as its domain. So, if f and g are two functions like this, like from f is a function from a to r and g is a function from b to r, then f plus g is actually defined only for those x common to a and b. That is, for any x, if you take here, f plus g of x is defined. Such a way we define f. So, even if f and g are real valued functions, f plus g is defined only on the common domain of f and g. Now, how f plus g is defined? F plus g of x is equal to fx plus g of x. Fx plus g of x. Similarly, f minus g is defined by f minus g of x is equal to fx minus g of x. K times f of x, the k f of x is defined by k into f of x. Similarly, fg of x is defined by f of x into g of x. And f by g of x, quotient function, f by g of x is equal to fx divided by g of x, but with only restrictions that those x for which gx is equal to 0 is not defined. That is, gx should not be 0 for defining f by g. These are some operations on the set of functions. For example, if you take fx is equal to x square and gx is equal to some 2x minus 3 are two functions from a to r, suppose a to r, both functions have the same domain r, then you can define f plus g by f plus g of x is equal to fx plus g of x, which is equal to x square plus 2x minus 3. That is a different function, x square plus 2x minus 3 plus g of x is a different function, x square plus 2x minus 3. That is also a function from a to r. If both f and g are having the domain a, f plus g is also has the same domain a, f plus g. Similarly, f minus g of x is x square minus 2x minus 3. That is, f minus g of x is equal to fx minus g of x. Here fx is x square, so x square minus 2x minus 3, or x square minus of 2x plus 3, which is x square minus 2x minus 3 for every x in the common domain of f and g. Similarly, you can define the quotient function f by g of x, which is f of x divided by g of x, which is equal to x square divided by 2x plus 3, but this is defined only for the point where 2x plus 3 not equal to 0. That means, when 2x plus 3 equal to 0, when 2x is minus 3, that is x is equal to minus 3 by 2. So here when you define this function, quotient function fx divided by g of x should not be equal to minus 3 by 2. This is quotient function f by g of x. F g of x, the product function, it is fx into g of x. Now this is x square into 2x plus 3, or simplifying you can write 2x cube plus 3x square. This is defined for every x in the common domain of f and g. There is no restriction here. But the restriction is only for quotient function, where it is defined only the points where gx not equal to 0. So you have to exclude this point minus 3 by 2 from the domain of common domain of f and g, only where this function fx by gx is defined. Okay, with this actually I am going to conclude what is function. We studied what is a function, domain, range, etc. and what are the different types of important types of real valued functions, constant functions, identity functions, like that we have seen. And finally we did some algebra on functions also. So with this I conclude. Thank you very much.